A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Today we will be talking about nanotechnology. That is actually a general lecture regarding the nanotechnology, the review of some old concepts, and a general discussion on nanotechnology is a type of revisions. So this lecture is a part of the lecture series regarding the course Nanophysics and Technology, having the course code of PHY445. Basically, nanotechnology, if you look toward the name, this means nano, and nano is equal to 10⁻⁹, and technology is the technology. So it's, from nanotechnology generally we means when we are working with matter down to the molecular level, or in other words we can say to the nano level. To create structure and devices, I mean when we are manipulating atoms and molecules at the nano level or at the atomic level, or in other words in molecular levels, so it is called as a nanotechnology. So such type of devices are called as the application of nanotechnologies, and the devices ranging from devices from 1 to 100 nanometer in size, with fundamentally new organization and properties and performance is a part of it. So this is general statement regarding the nanotechnology, and if we look towards it, it takes us to the realm of where the properties of material are dramatically different. The property are greatly linked with the structure of the material. Once we manipulate the structure, change the atomic position or modify it, so it can greatly enhance or modify the properties of the material. So it means in nanotechnology we can easily engineer the properties of materials by changing or by engineering the structure of the material. So it basically takes us where the property of materials are dramatically different, and definitely there are some other clues as well, which shows that property of the material at nano levels are much different than the properties of the material at bulk level. So it demands new tool and new understanding that why the property of the same material at bulk level are different from the property of the same material at nano levels. So this is basically the key way to revolutionize the industries, and having wide range of application with dramatic increase in the properties of the materials. So what are the basic challenges at nanoscales? So it means what type of challenges we face when we are manipulating the atomic or at molecular levels. So making nanomaterials is a bit can be done with different approaches, just like self-assembly. We have top-down and bottom-up approach. I mean we have experimental approach where we have top-down and investigate the properties of the material or the structure of material. At top-down approach, in some cases we have simulation where we do atomic arrangement and simulate or predict the properties of materials, and that is actually a type of bottom to top approach, that is called as bottom-up, and the previous one is called as top-down. So the other problem is that we need to characterize nanostructures, so in that leads to the matching and measuring small things. That is a bit challenging, that how we can characterize the materials at nano level and measure these small properties or these small things that are involved in this. So we need to understand the properties of the material, just like the length between the microvolt and single atom and molecules. So the properties of the material need to be evaluated, and that is important to be known. So that is so other thing is that the nano systems, where we have nanosystem integration and performance. So in that we assemble nanostructure into systems that is a high pay of area, and we need to have particular performance. We need to look toward the performance of that material and then investigate it. We have self-assembly, that is actually a nature approach to nanotechnology. Just like if we are looking toward the general case of photosynthesis center, where the optical receptors molecules are precisely aligned via spontaneous organization, and this alignment promotes collection, storage and utilization of light energy. I mean, the photosynthesis is a really interesting process where the solar energy is converted into food and the plants use it. So this is a type of 3D molecular arrangement promoting resonant coupling of this. So other thing is that we have living cells walls, that is actually basically a fluid molecular arrays rearranging in response to the chemical stimuli, and it changes in membrane structures influence intercellular diffusion. So that is important thing, that changes in the membrane structure influence intercellular diffusion. So this is a type of dynamic restructuring of molecular arrays providing adaptive response. So how we can build things at nano level, this is the most important thing. If we are looking toward the general measurement of the material or the general perspective what we are observing in our daily life, so if we have conventional machine, maybe the machine or engine, so that is built and assembled, and it is in the scale of millimeter to meter to millimeter. I mean the range of the material, I mean the size of the material is within meter to millimeter. So if we have top-down approach, I mean if we are coming toward the nano size or slowly in a decrease in size, so we have microelectronics, and in case of microelectronics we have another approach where we can be built in place, and the size in the microelectronics vary between 10 to 0.1 micrometer. So further development or further top-down approach is maintained, where we have self-assemble systems. That is actually a bottom-up approach. I mean we use simulation, that is in the range of 1 to 100 nanometer, where we can combine some atoms, or in other words we can have a unit cell and we can make a supercell from the unit cell. I mean we repeat the unit cell in 3 dimensions leading to the supercells. So this is actually a bottom-up approach. This is bottom-up approach, but the initial one, the example of microelectronics is the top-down approach. So this is 3 example, one of assemble, self-assemble, other one is top-down, and the third one is of bottom-up approach. And the bottom-up approach is basically the manipulation or the arrangement of atoms at the atomic level, and then that could be extended toward the supercell, and after that the property of that material is predicted, and finally the same material is synthesized in the lab, and the properties of theoretically investigated properties are compared with the experimental one. So the scale of the thing is like nanometers and more. So this is the normal scale. Regarding the nanoscale, we have things natural, just like ant, his size is 5 millimeter. If we have human hairs, its size ranges between 50 to 120 micrometer wide, and that is if we have flies, its size ranges between 10 to 20 micrometer. Coming toward the downside degree, slower in size, we have red blood cells with the white cells ranging from 2 to 5 micrometer and around 10 nanometer in diameters. So that is something about if we look toward the atoms of silicons, that is also some tenth of nanometer. The spacing between the atoms of silicon is at some tenth of nanometer. So if man-made things, this is something what we discussed about natural thing. If we are looking toward the man-made things, So that is the head of pin, that is 1 to 2 millimeter. And coming toward the lower decreasing size, we have micro electromechanical system, that is actually called as MEMS, and that size is 10 to 100 micrometer wide. And we have zone plate axis X-ray lenses. Its outer ring spacing is around 35 nanometer. And in the same way, if you look towards self-assembled nature inspired structure, that is actually many tens of nanometer, that is and the important thing is the carbon buckybars, and the carbon nanotube has a size of around 1 to 3 nanometer in diameter. So this is some data regarding the man-made things and the natural thing from the top down approach, that how the size of the things reduce and the properties are dramatically changed. So this is the scale anomaly, which describes the reduction in size and its corresponding size. So nanometer is actually new physics and chemistry that revolutionized material performance. I mean, as earlier we discussed that the property of the material are greatly improved at nanoscale, and that is not easy to understand because the same material behave differently at bulk and behave differently at nanoscale. So this is new phenomena associated with the small size, that is also called as quantized effect or quantum effect. So we have this is a pre-importance of surfaces and interfaces that is also responsible for that, and it leads to the new modes of electronic transports, radical changes in collective phenomena, and we have new chemical reactivities and new mechanical properties that lead to that. So this is something like we have a single molecule and how we can have the interaction between the single molecule, and this is the yield strength of a different material, just like nickel is compared, and we have bearing steel and some other material at nanoscales is 2 nanometer alumina particles whose yield strength is greatly improved. Carbon nanotube is the most important examples where its properties are greatly improved at nanoscales, and we have different structure of the carbon nanotube, just like armchair and zigzag. And in this top-down approach, we have the scale of nanostructure, just like we have 100 nanometer at top-down approach. I mean the size, and we have in bottom-up approach is 1 nanometer. If we are looking toward the size, so nanotube size. So this is something we are going to the extremes and improve the property, especially the mechanical properties and some other properties also, and it allows the material to be used in wide range of applications. So why nanomaterials are attractive? I mean, the question arises why we are studying material at nanoscales, and why it's so useful to us, and why it's so important to us that we are investing our energy, our research, and everything on the nanomaterials. So the answer for this question is the information technology, because we have high advancement in information technology, and that is possible only with the help of nanomaterials that are small in size and have drastically improved properties. So we have quantum electronics that have logic gates, and that have memories, and we have magnetic memories. The same material could be used for storing energy in the form of magnetic energy. Spintronics is also a most important field where we can manipulate the properties. So energy, because we are needing energy, so we can also get renewable energy sources from the nanomaterial. I mean, that can use to convert the solar energy into some other useful form of energy, and even use split the water into hydrogen and oxygen. So that is important to us. So in energy category, we have large scale and low cost nanoparticle based solar energy collections that have high efficiency, and solid state lighting. So it's also used, nanomaterial are also attractively used in health, where we have in situ drug delivery, and we need to diagnose, for diagnosis we need it, and for active monitoring we need the nanomaterials, and the performance of the material could be drastically improved when we are using the nanomaterial instead of bulk material. The same nanomaterial are widely used in environment because it's low cost, and it can use for environmental cleanup, just like the TiO2 material could be used for the degradation of inorganic material that are found in water and air. So this means just we can use the solar energy and the nanomaterials. So the nanomaterials automatically, the electron hole pairs that are created in the process that are automatically used in the degradation of inorganic material that are harmful for human life. So that is actually automatically degraded, and is that is divided into its parts. So that is why it is interestingly used in environment, and it has low cost and nanosensors areas for health and safety, and nanoparticle based waste destruction is also important. Just like I told you that we can destroy the waste or degrade the waste into its parts and convert it into useful constituent by using the nanomaterials. So in manufacturing it is also used, where we have a large area, we have bottom-up assembly for low waste and energy efficient manufacturing system. For that purpose we can also use the nanomaterial, and that is why these nanomaterials are so important to us. And the practical application of nanomaterials are huge. So we can list some of the application over here. So the top 10 nanotechnology products of several years is like we have high performance of Sekivax and breathable waterproof Zaki jacket, and there are huge range of applications that are used and that are utilizing the nanotechnology. So nanotechnology has great relation with the societies as well. It's not like that it is different from the, or it have no interaction with the society. It has interaction with society, and that is why nanoparticles has potential health risk. Just like properties changes with size. So can some size plus composition have adverse health effect? A question arises. So it's also implication for government regulatory systems. Just like same chemical with different forms, that's like carbon black, diamond, bakibas and nanotubes that have the same chemical and different size. Just like we have TiO2 and quantum dots of CDS and CDSE. So a question arises, how can nanoscale particles cross biological barriers? So this is also an important question, and that is related with the health issue. And what are the basically actually there is our responsibility and precaution to do with that, just like in the lab and in the factory or in the environment or consumer product. So how these two are related with each other. So nanoscale material categories are listed here. Just like we have naturally occurring ultrafine particles, whose virus is 100 the size of virus is 10 to 60 nanometer. If we look toward the bacteria, size is 30 to 100 micrometer, 30 to 10 micrometer, and this particles for this particle from desert is around 100 nanometer. Similarly, volcanic ash and forest where it's also come in the same range. So if we have ultrafine particles from established technologies or byproducts of conventional processes, that is like a combustion soot, its size is 10 to 80 nanometer. We have paint pigments, its size is 80 to 100 nanometer. Like welding fumes, we have the size is 10 to 50 nanometer. And similarly we have diesel exhaust particles, its size is 7 to 40 nanometer, and in case of carbon black for photocopier toner, its size is 10 to 400 nanometer. So similarly we have engineering nanoscale material that are actually the nanomaterials. So just like we have fluorines and buckybars, its size is 1 nanometer, and nanotubes size is 1 to 5 nanometer multiplied by 10 nanometer. And similarly quantum dot for medical diagnosis, the size is 5 to 20 nanometer. We have semiconductor wire for sensor, whose size is 10 to 100 nanometer, and its diameter is 1 micrometer. So this is something interesting what we presented about the nanoscale, where we have presented the thing by magnitude wise, that how the size of the different material matters and it affects the properties of the material. So this is some review about general nanotechnology. So thank you very much for now.